Alright, welcome to Mr. Allen's Finite class. Today's video is going to focus on combinations. Section summary. We're going to talk about what a combination is. We're going to look at the formula for combinations. We're going to look at this thing called Pascal's triangle, which is there to the right. And we're going to look at unordered partitions. Have you guys ever seen Blaise Pascal's triangle? Kind of looks like this. This top row, you'd want to call it maybe row 1. It's actually called 0 row. So it's a 1, and then this is 1, 1. Now this next row, you got a 1 here and a 1 here. This 2 comes from the fact that 1 plus 1 is 2. And then this 3 is 2 plus 1, which is 3. This 20, for example, 10 plus 10 is 20, whereas the 15 is the 10 and the 5. So any number within the triangle is the sum of the two numbers above it. Please note that the top row is 0. Okay, so combination. A combination of n objects is a way of arranging those objects without regard to order. This is the distinction between what we've been doing with permutations. Order does not matter. The formula for combination of n things k at a time is very similar to the formula that we use for permutations, except we put a c here for combination. In fact, you'll notice this n factorial on the top and the n minus k factorial on the bottom looks almost identical. The new twist, though, is this k factorial on the denominator. This k factorial gets rid of those selections that have the same elements but just in different orders, because we do not want to count those again. So let's look at an example. A group of 20 students enters a contest with 5 gift certificates as prizes. Each contestant's name has been put into a hat and 5 are going to be drawn. How many different ways can the 5 winners be selected? So I do need to kind of specify. Let's say that these winners can pick any of these gift cards that they want. Now notice that the total for each of those cards is the same, so it really doesn't matter who gets picked first or second. There's an example 1 flying up there. Okay, so solution. So we've got 20 students total. We're going to select 5. Order here does not matter because they all get the same value prize. We will use a combination of 20 things taken 5 at a time. Or, so here's the notation, combination of 20 things 5 at a time. Notice the 20 factorials on the top. 20 minus 5 factorial on the bottom with the additional 5 factorial. You do a little simplifying and you end up with a total of 15,504 ways to make those selections. So please go ahead and make sure you know how to use your calculator here. So if you're going to do the combination of 6 things 4 at a time, with your calculator you'll press 6, go to your math button or your probability button. Make sure you go to the combination, not the permutation, 4 things at a time, and you should get an answer here of 15. Then try 6 things 6 at a time, 6 things 1 at a time, and then 10 things 7 at a time. Now you may want to pause the video just to make sure you're getting this right, or you can wait and I'll just show you the answers and then you can check it with your calculator. But 6 things 6 at a time turns out to be 1. 6 things 6 at a time turns out to be 1. 6 things 1 at a time turns out to be 6. And then 10 things 7 at a time turns out to be 120. Now for this, most of the problems in this class are not going to be just, plug these in your calculator. You're going to have to do a little bit of translation. So for example, how many ways can 5 people be selected without regard to order from a group of 18? So we've got a total, our n here, I guess we could just call that n. We could say n here is 18, k is 5 because that's how many things we're picking. So it's going to be the combination of 18 things 5 at a time. So using your calculator, if you did 18 things 5 at a time, the answer turns out to be 8568. Alright, let's look at an example. 8 students from Mr. Allen's second period geometry class have been selected for a special incentive. If the class has 13 females and 16 males, And there's an additional restriction. The number of females must equal the number of males. How many different ways can the 8 students be selected? So I want to make a couple of notes here. If there are 13 females and 16 males, how many students are there total? Now, hopefully you're thinking 29. If we are picking 8 students and the number of females and males must be equal, then how many of each do we have to pick? Hopefully you're thinking 4 and 4. So let's look at how the solution will work. So we're picking 8 from a group of 29 total. That's that 29 total that we found. The order in which the winners are selected is not important here. We're just picking 8 people. The number of females must be equal to the number of males, so that's the whole 4 males and 4 females thing. And we're also going to use something called the fundamental counting principle, which I'm sure you're familiar with. What we're going to do is we're going to do the number of ways to select female times the number of ways to select a male. So here's how that works out. There are 13 females, we're going to pick 4, and we have to pick 4 males. So when you see the word or think the word and, I want you to be thinking of times. So 4 girls and 4 boys, so we're going to times those together. This is that fundamental counting principle, and it turns out that there are 1,301,300 ways to make this selection. So let's look at another example. Same situation, just a little bit different. Again, we've got 8 students that we're selecting, 13 females, 16 males. The additional restriction here is that the number of females must be at least 6. So how many ways can the 8 be selected? So at least 6 females. So let's look at the solution. We are picking 8 from a group of 29 still. The order in which the winners are selected is not important, so that's going to make this a combination. Since we have to have at least 6, that implies that we're going to have 6 females, or 7 females, or 8 females. Now just a second ago I told you to associate the word and with times. I want you to associate the word or with plus. Okay? Things are a little bit more complicated here, so make sure you follow this. Remember, there are 13 girls. We could pick 6 of them, and in that case we would have to pick 2 boys. So this is the girls, these are the boys. Or we could pick 7 girls and 1 boy. Or, so there's or again, we could pick 8 girls and no boys. And then you could plug this into your calculator, this big expression, and it turns out to be 234,663 ways. Now I want you to try this one on your own. It says 6 students from Mr. Dablow's 3rd period class, algebra class, have been selected for a special incentive program. The class is made up of 12 females and 9 males. An additional restriction has been placed on the selection. The number, there may be no more than 2 males. How many different ways can 6 students be selected? So, if you want to pause now, that'd be a good thing. I'm going to give you the answer, but I'm not going to show the work. We've got 6 students being selected from a group of how many total? And the number of boys can be no more than 2. So we could have no boys, 1 boy, or 2 boys. Now don't forget though, we still have to take into account the girls. The final answer here is 25,872 ways. 25,872 ways. Alright, back to our good friend Blaise Pascal, creator of the Pascal's triangle. He lived from 1623 to 1662. He was French, he was a mathematician, he was a physicist, he was an inventor, he created the first mechanical calculator, he was a Christian philosopher. We've got a picture of him over here. So, Pascal's triangle. What is the connection between Pascal's triangle and combinations? Well, let's go ahead and go through and build it again. So if I have 1, 1, 1, 1, 2, 3, oops, I screwed that up. That should be a 1 right there. 1, 3, 3, 1, 1, 4, because 3 plus 1 is 4. 3 plus 3 is 6. 4, 1. This is Pascal's triangle here. Now just humor me here with your calculator. Do the combination of 4 things 0 at a time. What do you get? How about the combination of 4 things 1 at a time? How about the combination of 4 things 2 at a time? Or the combination of 4 things 3 at a time? Or the combination of 4 things 4 at a time? Well, if you did those with your calculator, you found out that the combination of 4 things 0 at a time is 1. The combination of 4 things 1 at a time is 4. The combination of 4 things 2 at a time is 6. And then 4. And then 1. It turns out that Pascal's triangle will actually generate combinations. Okay, so let's look at an example of this. Alright, so using Pascal's triangle, now if you haven't done it, write it down. And I want you to write Pascal's triangle, do at least the first 7 or 8 rows. Okay, do the first 7 or 8 rows. And I want you to find the combinations using Pascal's triangle. Don't cheat and use your calculator. Alright, now I'm going to show you this worked out here. So the top row of Pascal's triangle would be 1, 1, 1, 1, 2, 1. I can add here, I promise. 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and then 1, 7, 21, 35, 35, 21, 7, and 1. So, 6 things 2 at a time, you go to the row with the 6's in it. And this is 6 things 0, 6 thing 1, 6 thing 2. So the answer for this one is 15. 3 things 1 at a time, you go down to the 3's. Okay, so 3 things 1 at a time, that's 3. 7 things 4 at a time, go down to the 7 row. So that's 0 at a time, 1 at a time, 2, 3, 4. So the answer is 35. Feel free to check that with your calculator. Alright, last thing. How many ways can a professor divide her class of 32 students into 8 groups of 4, each without regard to order? So here we've got 32. We're going to use all 32 students, but we're going to put them in groups of 4, and it doesn't matter the order in which they're placed in these groups. To do so, we're going to have to use another formula. This is the unordered partition formula. It's kind of different. You'll notice we've got some factorials going. This is the total number of things. This is the number of groups. This represents the number of things in each group. And then you'll notice we've even got a little exponent here going. So, N here is 32, M is 8, K is 4. So what we're going to do here, our N is 32, is 32, so that goes on the top, factorial. We're doing 8 groups, so that's 8 factorial. And then in parentheses, we're going to do the number in each group, factorial, and then we're going to take that to the 8th power. So, now be careful when you plug this into your calculator. You're going to have to make sure you put some parentheses around this bottom, and this again here, don't forget that's an exponent. And when you work this out, it's going to be really big. In fact, it's so big your calculator can't show you the complete answer. It turns out that it's roughly 5.93 times 10 to the 19th. In other words, you would have to move this decimal 19 places over to write it out. That's how big, that's how enormous that particular number would be. And that, folks, will do it. Have a good day.